This is tutorial 8, linear algebra, eigenvalue, eigenvectors, and this is question 7 from example 2 of Lay's 5th edition. Now, we are given a matrix A, and we are told that A equals to PDP minus 1, where P is this matrix here, and D is this diagonal form. Therefore, we can actually immediately conclude that lambda equals to 5 is an eigenvalue, lambda equals to 3 is an eigenvalue, and correspondingly this is P1 and this is P2. This would be P1 equals to 1 minus 1 for the eigenvector corresponding to lambda equals to 5, as well as P2 equals to 1 minus 2. Well, let's try. If we have a matrix A and we multiply A by this, we should, if this is a real eigenvector and eigenvalue, then we should get, well, I would think that we should get 5 and minus 5. Let's try. So this was our A, this was our X, and we expected it to be, if X is an eigenvector, it will be lambda X. And in this case, our input X is P1, the eigenvector, and lambda is equals to 5. So by brute force, we show that this is true, and we can conclude that. Right, the other thing, when we are given eigenvector and eigenvalue matrix, we will often want to say that A equals to PDP minus 1. Why is this so? Well, we actually start with A of P1 equals to lambda 1 P1, and A of P2 equals to lambda 2 of P2. Now, if we collapse P1 and P2 to be this form, then we can say that this is A times P matrix. And then if you observe that the first column A times the first column of P will be equals to lambda 1 P1, and A times the second column of P2 will be lambda 2 P2. Now this is equivalent to the matrix P times a diagonal matrix D, which is consisting of lambda 1 and lambda 2 in the diagonal. So you can actually see for yourself that this is so. Alright, when you open up P times the D matrix. Now, if P is invertible, this is an important case, implying that P is full rank, and it has a complete set of bases for Rn. So here n is 2 by 2, n is 2, and we are having A is a 2 by 2 matrix, and therefore we need P to have 2 independent eigenvectors. And then now, if this is so, then what we get is that we will do A times P minus 1 on the left hand side, and therefore we have P times D times P minus 1 on the right hand side. This reduces to I, and therefore we now get the famous equation A equals to P times D times P minus 1, where P is the columns of eigenvector, and this is the diagonal, is a diagonal matrix consisting of the eigenvalue, and this is of course the inverse of the columns of eigenvectors. Now, once we have this equation, we can actually show that, well, I'm going to show you something interesting. Now, we're trying to move the P's from the right hand side to the left hand side. So to get that, it will be p minus 1 p, because what you are actually trying to do is p minus 1 times p times d times p minus 1 times p. You're introducing these two matrices on the left hand side, p minus 1 on the left of A, p on the right of A. So we must introduce p minus 1 on the left of this guy, p on the right. Now this reduces to I, this reduces to I, therefore p minus 1 AP equals to D. So this is, we can diagonalize a matrix A into D by pre-multiplying with p minus 1, post-multiplying with p. So this is the nice picture that we have of these equations, right? But we haven't figured out how to do the questions yet, so we proceed. We start with this equation, and then what we are going to show you is what happens when we have A times A. Then we have PD p minus 1 times PD p minus 1. So we can open up the bracket, and then what happens is that this matrix multiplied by this matrix become identity. So we have PD square p minus 1. And then if we have A cube, then we will show, it can be shown it will be PD cube. Now, the interesting thing, of course, is that when D is diagonal, then it is very simple. For example, D equals to, let's just try D11, D22 with 0. So what happened in D square is D11, 0, 0, D22 multiplied by D11, 0, 0, D22. You realize that this guy is equals to D11 square, 0, 0, D22 square. And then you can try dk, and you can conclude it will be D11k, 0, 0, D22k. Therefore, AK is equals to P dk P minus 1 is equals to, and then we can write out the equations 1 minus 1, 1 minus 2, 5k, 0, 0, 3k, and then the last matrix is 1 minus 1, 1 minus 2, inverse. Alright, so this is what we get, and I'm happy to leave the answer as this is. Of course, if you want to open it up, you can't. Right, that's all. Thank you. Maybe we stop for a while and we try for the MATLAB version of things. So in MATLAB, I want to show you that if A is equals to this matrix, which is 7 minus 4, 2 and 1, and then I get P and D equals to Argand decomposition of A. Let us see what is P and D. So I've typed A equals to this matrix, 7, 2 minus 4, 1. I type P comma D equals to Argand decomposition of A, and we get P equals to this. So P equals to 0.707 and minus 0.707, and the other one is minus 0.4472 and 0.8944. What about D? D is equals to 5003. So it looks like D is what we have, but what about P? So if you look at this very carefully, then isn't this alpha minus alpha? And the other guy is minus beta, and this should be 2 beta. Now if you compare with what is given to us, the eigenvectors of P are 1 minus 1 and 1 minus 2. Now, therefore, what what MATLAB did was it reduces this guy into the normal equations. So it reduces this guy to the normal equations. That means the length is 1. What about this guy? So it used minus beta and 2 beta, while in the equations that was given to us, it was 1 minus 2. So what's the difference? Well, if you multiply by minus 1, you will get minus 1, 2 here. And then if you normalize it, you will get exactly minus 0.4472, 0.8944. So what happened is that MATLAB basically produces a normalized eigenvector, and it doesn't matter where the eigenvector is pointing in the sense of positive or negative direction, okay, as long as it's pointing to the direction. So don't be confused with this. The numbers of the eigenvectors of P as compared to us, although they look numerically different, they are actually still eigenvectors. They are just normalized eigenvectors, and in here they are pointing to a different, they are pointing to the opposite direction.